In this lecture, we're going to have a look at the properties of operational amplifiers, or OpAmps. They're one of the most important electronic components, can be used for a wide range of uses. But obviously we have to understand their detailed properties if we're going to use them correctly. So as the name suggests, operational amplifiers are just general purpose amplifiers. Now you might define ideal features for them. The ideal features might be an output resistance of 0, so no resistance at all to the current flowing out or the voltage coming out. Input resistance should be infinity, so that it doesn't draw any current from the previous part of the circuit. It just takes the voltage signal in, with an infinite differential voltage gain. So differential voltage gain means that it amplifies the difference between the plus rail and the minus rail. Now, of course, this in reality, real performance is not as good as that. But what we see with op-amps really is what is often known as the two golden rules. The output attempts to do whatever is necessary to make the voltage between the two inputs zero. So that's really how the circuit functions. And the inputs draw effectively no current, so it really has a very high input resistance. So in previous modules you will have been introduced to the operational amplifier, op-amp. You will have seen circuits like the inverting amplifier shown on the left of this slide, where the V out over V in is equal to the ratio of the two resistors R2 and R1, but we've got a negative sign there to show that it inverts the signal. You have the non-inverting amplifier on the right, so V out over V in is again related to that ratio, but we've got that extra term of +1 on the end. And you should also be aware of these other forms of it. We've got the difference amplifier, so this is where I've got two voltage signals applied, V1 and V2 now. V1 traditionally is placed on the negative rail, but you can change this around as well. You've got a slightly more complicated resistor network, but the V out is proportional not only to the ratio of the two resistors, but actually V2 minus V1. So it amplifies the difference between V2 and V1. And then we can also use these op-amps as what we call an instrument amplifier. This is a slightly more complicated circuit. And again, we have an output resistance which is proportional to the differences between the two. But what you can see here is that both my input signals, V1 and V2, are applied to the positive terminal of the first group of op-amps. So it's a slightly different circuit to the difference amplifier, but it's commonly used for so-called instruments where I might be receiving information from a number of sensors, for example. And I can fuse those together through this type of circuit. So I get a slightly more complicated operation in the instrument amplifier, but again it's a very useful circuit that I might use in some circumstances. Now, almost all of these op-amp circuits rely on the concept of feedback, where the signal or voltages from part of the circuit are fed back to earlier in the circuit, and this is used really to stabilize the operational amplifier. So we're going to look in more detail now at this concept of feedback and try and understand actually a little bit more in detail about how it works. So of course there are two polarities of feedback, negative feedback and positive feedback. Now, generally speaking, positive feedback, where the signal comes round, there could be a feedback gain factor F, as shown in the right-hand diagram, and then that feedback voltage acts in a positive way to reinforce the signal. So the signal becomes larger every time the feedback goes around that circuit. And these are primarily used in oscillators, which are actually an interesting class of analog circuitry. We're not going to cover them in this course, but they are very useful actually in a large number of applications. As a way of generating waveforms, for example. But what we're more concerned with in this course is negative feedback. So the signal is fed back through the feedback network and it acts in a negative way to subtract away from the incoming signal, and that's fed round. This creates actually a more stable situation and it enables us with the op-amp to control the amplification through the resistor networks that we're going to put around the op-amp. So we're going to concentrate really on this negative feedback concept. So let's look in more detail at this concept of negative feedback. So at the top left hand side I've got my sort of fundamental diagram, if you like. I've got an op-amp in the middle with an amplification of A. I've got a feedback network with a feedback factor of F, and that's fed back in a negative way. My signal comes in from the left, and the signal that actually reaches the op-amp is traditionally labeled SE, which is the so-called error signal, but actually it's the subtraction after the feedback network has had its effect. Now the output signal, S out, is actually always equal to A times the error signal, SE. That's the fundamental property of the op-amp. And what I'm trying to do is I'm trying to reduce that complicated circuit with the different components, the op-amp and the feedback network, down into an equivalent circuit, and I'm trying to obtain the term AF, if you like, which is the gain of the whole circuit now. So if I go back now to the right hand side where I've gone through the proof really of how I'm going to derive that, S out is equal to A times SE. But I actually know what the value of SE is. That's going to be equal to the S in, the signal in, minus SF, which is the output from the feedback factor. And I know that SF itself is equal to F times S out, where F is the feedback factor. So that gives me a form really for S out. And now if I want to work out the gain for the whole circuit, AF, that's S out over S in by definition. And I can replace in there, and I will, if I manipulate that maths there, I will end up with the formula in the red box at the bottom, that the AF, the gain of the whole circuit, is equal to A over 1 plus AF. And in most cases, for most values, that's going to be more or less proportional to 1 over F. So the gain of the op-amp doesn't play much of a role, if any, in the overall gain of the circuit. It's the feedback network which dominates. And that feedback network, of course, is created by the resistors in the circuit in most cases. And those are very easy values for me to choose, and they're very reliably manufactured resistors, so that I can predict very easily what that gain is going to be of the whole circuit. So that's one of the most attractive parts of these circuits, is that actually it's the feedback network which controls the gain, and that is very predictable and very easy for me to manage and design. So in this general circuits, the general feature of this feedback situation is that the feedback network is the one that dominates over the amplifier, and that's what we see in real life with op-amps. But if you look at this in more detail, really, as shown in this slide, on the top left we've got a diagram there. That's the diagram we had before, showing the negative feedback network, where F is the feedback factor. So let's imagine what happens if the amplifier is slightly more powerful, say, or slightly less powerful. So we can represent that mathematically by saying that the amplifier gain now changes to A plus delta A or A minus delta A. Then the actual amplification of the whole circuit, A little f, is given by A over 1 plus AF, as we had before. If I now replace A with A plus delta or A plus minus delta, then I can multiply that all out again and work out the effects of those deltas. And what we see really is that as long as that multiple of AF is greater than 1, then actually the gain is still dominated by the feedback. So what that means is that any small manufacturing changes in the amplification of the op-amp, due to the circuits being microscopically different, for example, is going to have absolutely no effect on the circuit. And that's really very useful characteristic, because the errors in manufacture of a resistor are infinitesimally small. The resistors are incredibly reliable in terms of manufacture. Their values are always very precise. Whereas transistor circuits, which essentially is what the op-amp is, do vary. So that could lead to unwanted variations in the circuit property. But here I'm pretty safe, because I know that my answers are in terms of the actual reliable resistor device. Another advantage of this negative feedback circuit is actually that it eliminates distortion, or it greatly reduces distortion. So imagine if the basic amplifier did have a bit of distortion inside it. So for example, on the right hand side we've got an input signal coming in as blue on the right, comes in. If my gain was distortive, my output signal might no longer be a pure sine wave. But with feedback, actually, the gain is not really affected by this amplifier distortion, because the gain of the circuit is determined by the resistor network, for example, with the op-amps. So as long as they don't have any distortion, then my overall circuit won't have any distortion as well. So it reduces the effect of distortion, provided obviously there's a limit to how far we can go with this. If the amplifier is really distortive, then obviously that would dominate. But for minor distortions, actually it has very little effect, because actually it's the feedback circuit which dominates in terms of generating the output signal. A third advantage is so-called noise rejection. So if I imagine I have a badly constructed amplifier circuit which generates noise inside itself, so there may be some loose connections inside the amplifier, for example, which is generating a lot of unwanted electrical noise, then if that amplifier was just there on its own without feedback, then that noise would be amplified by the properties of the amplifier, and I'd end up with a very noisy output signal. When I've got a feedback network in place, though, it actually works in a different way. Then the feedback network, which is simply resistors, that doesn't have that source of noise. So that noise that's coming in, from this noise internally in the amplifier, is actually rejected, really, if you like, or cancelled out as it comes around via the loop. So we don't see any amplification factor for that noisy amplifier, which is a great benefit. And that means that there's an inherent sort of noise limitation effect of this feedback network. So we've seen that feedback can be a very positive thing. It enables us to predict very accurately what the gain of the circuit is. It reduces noise and so on, and some of the other advantages we've seen. But of course, nothing is free, and the downside of feedback is that it reduces the gain. So the amplifier circuit, in our case maybe an op-amp or a transistor amplifier of some kind, may have a very high inherent gain. We're going to reduce that with the feedback, but the circuit's going to become a lot more stable, and I've got some of the benefits that we've already looked at. So if that feedback has reduced the gain too far, then we might have to go to a two-stage design where we have a preamplifier to boost the gain before coming into a power amplifier. So we need to understand that this feedback is great. Negative feedback is really useful in amplifier circuits, but there is this reduction of the gain as a major downside. And of course, that if we did generate positive feedback in some way, then we're going to end up with that oscillation, which we want to avoid in most cases. Let's move on now and have a look at the frequency behavior of these amplifier circuits. So if I imagine myself with an amplifier, just a basic simple amplifier where I've got a signal in and a signal out, then generally speaking what I'll get as a function of frequency, or I can either express that in terms of angular frequency, omega, or I can do it in terms of hertz, for example, but I'll get a graph a bit like I've drawn at the bottom here. So I'm going to get a flat section where the gain is fairly constant. So I've got showing the gain in decibels on the vertical axis, and then at some point the gain is going to begin to reduce, and generally speaking I'm going to see a slope there of 20 decibels per decade. This is the same slope that we saw in the filter case, and the point where it changes is referred to as the pole, the first pole, P1. And in general, my amplification factor is going to scale with frequency in the way that's shown there, and I'm going to end up with a frequency term as shown in the red box, where my frequency reduces as I go up in frequency after the pole. When I then include the feedback network, F, then my gain in general will be reduced. So if I look at the diagram shown highlighted at the bottom there, then my ALF is the gain from the basic amplifier, the one that we saw on the previous slide. Now that I've got my feedback in, I'm going to be operating on the red line, so my gain is going to come down, and the point at which it changes though is going to be slightly to the right. So my pole is now moved slightly to the right. The slope, though, going down towards 0 will be the same 20 decibels per decade that I see with all of these types of circuits. What I see, though, is that my region in which the gain is constant, the flat band frequency range, that's extended. So with the feedback amplifier, I reduce the value of the gain, but the frequency range for which the gain is constant is greatly extended. And again, that's also a very useful characteristic, because usually I want that frequency range with the same gain, the flat section of the graph, to be as wide as possible. So this is another advantage of an amplifier with a feedback network. Remember, if I wish to boost the gain, I can always boost it by having 2 or more stages, but I still would keep this wider range, which is very useful. So again, this is another benefit of the feedback mechanism. It gives me a wider range for which the gain is constant. Okay, now we've looked at the benefits of feedback in terms of circuits. I want to move on now and work towards understanding a bit more about the difference amplification, amplifying the differences between 2 signals. And remember, that's what I'm always doing with an op-amp. I've got a non-inverting input and an inverting input. So this is the circuit design of perhaps the most classic of all op-amps, the 741. This can be made with various transistor technologies, but usually it's made with a BJT based signal technology, and here that's what I've shown here. And what you can see in the diagram is that my inverting input comes into Q2 and my non-inverting input comes into Q1. So those inputs that I see as the inputs to the op-amp, this is what happens to them. They go into the base of these 2 transistors, and that turns those transistors on. And then we need to understand what happens when that occurs and how we make that work. But really what we're doing is we're seeing the difference between those 2 signals, and that's the basic function of the op-amp, of course. And of course I can build op-amps with other types of transistors as well. So this is an op-amp based on a MOSFET type transistor, and again it's more or less exactly the same concept here. Actually, I've got two inputs, the negative and the positive. They both go into the gate of these 2 transistors, and then that creates controls the currents in those 2 lines of circuitry that go up through M3 and M4. So it's a very basic similarity between these 2 types of circuits, and all of them really are based on what's called a differential input stage, where I feed the signal into 2 different transistors that are connected, if you like, in 2 parallel lines, and that then controls the current flowing down each line, and then the relative effect of those is going to control the signal that comes out. Okay, now we're going to look in more detail at some of these non-ideal performance things. We're going to introduce a couple more that we haven't thought about yet. Slew rate, for example, and the input offset voltage. Those are both important things that we need to think about for these kind of circuits, but particularly op-amps. We're going to look at common mode rejection ratio and the power supply rejection ratio as well. So the slew rate is one of the most important limitations of an op-amp, and it's essentially the limited rate at which the output can follow the input when the input has a relatively large swing or a relatively large change, and this causes distortion. So if you think about a square wave input, for example, that has almost an infinitely fast, sharp rise, and in fact the output will struggle to follow that very fast rise. So instead of getting a perfect square wave, what you tend to get is a triangle wave, or it'll cut the corner of the output. So on the right hand side I've tried to show that. So the input signal is a perfect square wave. What we should really expect is a slight rounding of that due to the frequency response limitations. We know that there's a limited flat band rate. But what we find actually is that you actually get a much more dramatic triangle edge, and that's due to the fact that this effect called the slew rate. The amplifier is struggling to cope with that very rapid change of the square wave. If we're thinking about sine waves, what we tend to find is that it's actually more about the distortion of the wave, and obviously this affects high frequency sine waves more than it does low frequency waves. So at low frequencies, the amplifier is easily able to cope with the up and down of the wave, but at high frequencies it can't, and the wave is distorted, and the output is a little bit delayed as a consequence of that. And we measure the slow rate in terms of the voltage over time, so it's volts over microseconds is the usual units that's used. And if we want to understand the origin of this limitation, the slow rate limitation, then actually we have to think about the circuitry that's inside our op-amp. We saw already that that has a number of different stages. It has a differential stage at the input, where the V in minus and the V in plus, the two minus and plus inputs are combined and come together. And actually what we've seen is that differential stage, essentially what happens is those signals turn on the gates of the transistors, and that then allows a current to pass down through the chain inside those differential stages. And there's simply a limit really with how much charge, how much current the power supply can pass down through those transistors. And it's that's really the limitation, essentially, is the ability of that differential stage to pass current. And that limitation then affects the signal that comes onto the next stage, the amplification stage, regardless of whether it's a common emitter BJT or a common source MOSFET. That limitation on the current in the differential stage will limit the signal coming into the amplification stage and then into the power amplification stage at the end. So it's actually this limitation of the differential stage which causes this slow rate problem. And the slow rate obviously is this rate of change of voltage with time. So as we've seen, this slow rate limitation is due to the limited current that the differential stage can pass down into the amplification stage. And essentially that limited current can't charge the capacitors that are built into the amplification stage as quickly as we need to. So this causes this lack of response, where we see the square wave become a little bit more like a triangle wave on that corner, as shown in this diagram. This is actually regardless of the feedback loop that I may have in the circuit. So it's nothing to do with the feedback network that I have in the op-amp circuit, for example, in most cases. It's just an inherent problem inside the op-amp, and it's actually the same whether you connect that feedback or not. Another practical limitation we see is what's known as the input offset voltage, and this again actually comes about from what we need to do to make use of this differential input stage. So that's what I've shown in the diagram here. I've got two BJTs as part of my differential input stage. I've got a positive input and a negative input, and they feed the gate of those transistors. Now, regardless of the properties of those transistors, I need that current. I need that current to turn on the gate of the transistors. So this small current is a DC current, and actually this causes a voltage drop in the resistor network, the feedback resistors, regardless of whether I have a signal there or not. So at the output of the op-amp, we always see a small DC voltage that's generated by this current that's flowing into these signals, even when the input is zero. And we can measure that in our circuits, and this is the sort of DC residual voltage at the output. And this is a problem that it's not particularly significant, but that voltage is always there. So is there anything I can do about this input offset voltage and this voltage effect? Well, there are some tricks that I can use to reduce the effect of this. So for example, I've shown an op-amp circuit here with the resistor network R1 and R2, and this offset is generated really because those resistors exist. There's going to be a current flowing into that side, and that generates a voltage, which then produces a voltage in the output. There's nothing I can do about that. Because it's a differential effect, the op-amp's a differential amplifier, amplifies the difference between the plus and minus. The only way that I can get over that is to have a voltage at the plus side which is equal in value to that at the negative side. So I can actually introduce a network of other resistors which actually mimic the parallel effect of R1 and R2 on the positive side, and that will then reduce that offset to as close to zero as possible. So there are things I can do like that, where I then reduce the effect of these offset voltages, but it's only a reduction really. It's very difficult to get this down to completely to zero. And I just want to emphasize also that this is not just a problem of BJTs. We still get this problem even with MOSFET type devices as well, although you can sometimes reduce those again by trimming the circuit resistors to be as accurate as possible, but it's still inherent. There is always a very small offset voltage at the output when the signal is zero, which is obviously it's not something we want, but it's hard to get rid of completely. We've talked already about the common mode rejection ratios and how we want to make sure that the common mode is reduced as close as possible to zero. So we're looking for a very low value of the common mode gain and a very high value of the differential mode gain. So we've defined already the common mode rejection ratio as those one divided by the other, and then the decibel calculation. The inherent origin of these actually is really caused by very slight mismatches in the transistor design of the differential input stage. If you look at this design here, for example, these are it's a MOSFET type based design. It's the same thing that we looked at before. The negative signal and the positive signal both come directly into the transistors. They come into M1 and M2. They switch on, and that then creates currents, and the difference between them will affect the current flowing down through that line. This is all assuming, of course, that M1 and M2 are perfectly identical. Any slight mismatches between those transistors will increase the possibility of there being the common mode problem. So I want those to be as identical as possible, but inevitably there are some small differences, and that causes these common mode type situations. But it can be reduced to be very great. So we want this common mode rejection ratio to be very high, and you can see that I've done a little calculation there when I've said that my differential gain is 10 to the 6, but in decibels, but my common mode gain is 10. So I'm looking there at a decibel of 100 decibel common mode rejection ratio. And the last problem that we're going to look at is so-called power supply effects, if you like. So we're looking here at the power supply rejection ratio. So this is the sort of circuit that that's built inside a block version of my OpAmp circuit, for example. On the left, I've got my differential stage with the negative and positive inputs coming into those transistors. In the middle, I've got some amplification, and then generally I've got a power amplifier. All three of those blocks of circuits are going to require power supplies, and what we're assuming in most of our circuits is those power supplies are completely perfect and they give a perfectly stable DC supply. In practice, that's not usually the case. Actually, there's usually a small amount of so-called ripple, slight variation, particularly bad in mains connected amplifiers. It's much less of a problem in battery supplies. But what we were hoping is that any small changes, any of that ripple, has a very small effect on the output voltage. So we define this idea of the power supply rejection ratio, and that's actually the sort of decibel calculation, if you like, of delta V supply over delta V out. So we're looking for that to be as high as possible, so that I get any variation in the supply produces a much smaller variation in the output. So I'm looking for a very high value of PSRR, power supply rejection ratio. Okay, so in this film we've covered a lot of ground. We've looked about OpAmps. We've reminded you about some of the things that you would have learned about OpAmps in other courses. We've looked about in a lot more detail about how that feedback network works and the advantages of feedback. We've looked at how you derive the gain for the negative feedback. Remember, it comes back from those properties of those feedback resistors in that network of resistors around the OpAmp. And we've looked at non-ideal performance, things like the slew rate, the offset voltages. We've looked at common mode rejection ratio, power supply rejection ratio, and so on. And we've had a look at the frequency response, which is also very important. And we had that very key graph where we showed that the an op-amp with no feedback has a very high gain, and it has a pole that then reduces with 20 decibels per decade slope. When we introduce the feedback, we reduce the gain, but we widen that flat section of the graph where the feedback is more stable. So we've gone through a lot of ground, and this will give you hopefully a really good understanding of the important properties of op-amps, which are a very important circuit element in many analog circuit applications.